In this video, we're going to look at the flux form of Green's theorem. The second form of Green's theorem relates the flux across C to a property of the vector field within R that will produce the flux. We're going to let C be a simple closed smooth curve oriented counterclockwise that encloses a connected and simply connected region R in the plane. If we assume that my vector field F is specified by the vector with components Fg, where F and G have continuous first partial derivatives in R, then the closed integral over C of F dotted with N ds is equal to the closed interval over C of f dy minus g dx. This can also be written as the double integral over R of the partial of f with respect to x plus the partial of g with respect to y dA. The first integral, the integral where I'm dotting f with a unit normal vector, gives me the outward flux. The second integral is a different form of that same integral. It is also the outward flux. And the third integral has an integrand that describes the flux across C, where n is the outward unit normal vector on my curve. The sum of the partial of f with respect to x plus the partial of g with respect to y is called the two-dimensional divergence of the vector field. The divergence of a vector field measures the flux of one particular vector field at a point P. If the partial of f with respect to x is greater than 0 at that point P, it indicates an expansion in the vector field in the x direction. If it's negative, it's going to indicate a contraction of the vector field. If the partial of g with respect to y is greater than 0 at P, it indicates an expansion in the vector field in the y direction. The result of the sum of the partial of f with respect to x with the partial of g with respect to y being greater than 0 means that there will be a net outward flux across a small circle enclosing P. Essentially, this says that a positive flux points outward on my region. If the divergence of f is 0 on the entire region, where f satisfies the flux form of Green's theorem, then the outward flux across the boundary is 0. Vector fields with 0 divergence are considered to be source-free. Positive divergence throughout R means positive flux across C. The vector acts as a source in R when this happens. A negative divergence throughout R means a negative flux across C. In this case, the vector acts as a sink into R. So, two-dimensional divergence of a vector field, where the field is given by a vector with components f and g, is the partial of f with respect to x plus a partial of g with respect to y. If the divergence is 0 throughout a region, the vector field is said to be source-free on that region. Let's work an example. I'm given the vector field f is equal to a vector with components y and negative 3x, and R is a region bounded by y is equal to 4 minus x squared and y is equal to 0. I want to compute the two-dimensional divergence of the vector field, evaluate both integrals in Green's theorem, and check for consistency. And then I want to state whether the vector field is source-free. I'm going to first compute the divergence. The partial of f with respect to x plus the partial of g with respect to y is equal to 0 plus 0 or 0. I'm going to sketch my region because it's going to give me a better idea of what I'm trying to do. I have a region bounded by a downward opening parabola with a vertex at the point 0, 4, and it crosses the x-axis at negative 2 and 2. And on the bottom, my region is bounded by the x-axis between negative 2 and 2. I have two r vectors on my boundary I need to construct. R sub 1 is the boundary that follows the downward opening parabola. It is a vector with components t and 4 minus t squared. F of 1 is equal to the vector with components 4 minus t squared and negative 3t. R of 2 is the vector along the x-axis between -2 and 2. That vector is given with components t, 0. F sub 2 is a vector with components 0 and -3t, for t lying between -2 and 2. So that the closed integral over c of f dotted with n ds is equal to the closed integral over c of f dy minus g dx. This becomes the ordinary line integral from -2 to 2 of the quantity 4 minus t squared times -2t minus -3t times 1 dt, plus the integral from -2 to 2 of 0 times 0 minus -3t times 1 dt. This becomes the integral from -2 to 2 of the quantity -5t plus 2t cubed dt, which is equal to 0. This is a source-free vector field because the divergence is 0. I want to do another example where I want to use Green's theorem to evaluate the line integral given by the closed integral over c of the quantity 2x minus 3y dy minus the quantity 3x plus 4y dx, where c is the unit circle. My closed integral over c of f dy minus g dx is equal to the double integral over r of the partial of f with respect to x plus the partial of g with respect to y dA. Notice that my f is the quantity 2x minus 3y, and my g is the quantity 3x plus 4y, so that the partial of f with respect to x is 2, the partial of g with respect to y is 4, and my double integral over r of the partial of f with respect to x plus the partial of g with respect to y dA becomes the double integral over r of 2 plus 4 dA, which is equal to 6 times the area of a unit circle, or 6 pi. Green's theorem is very powerful, and one of the things that the Flux form allows us to do with a little bit of cleverness is compute a double integral over a geometry that could be simple or complex by cleverly choosing the functions I want to use for f of xy and g of xy that will simplify my work. So here's an example. I want to use the Flux form of Green's theorem to evaluate an integral over a given geometry. The double integral over region R has an integrand given by 4xy plus 3y squared dA, and my geometry is a triangle that has vertices at the points 0, 0, 1, 0, and 0, 1. Now, just as a reminder, the Flux form of Green's theorem tells me that I can rewrite a double integral over a region R as a line integral, where the integrand of my double integral is the partial of f with respect to x plus the partial of g with respect to y dA, and I can reconstruct that as the line integral over a pathway of f dy minus g dx. So let's see how that can apply. I want to choose a function of f and g that will match the given integrand of 4xy plus 3y squared to partial of f with respect to x plus the partial of g with respect to y. Don't overthink this. I'm going to let f of xy equal 0 and g of xy be 2xy squared plus y cubed. I do this because it will significantly reduce my work. This means that my double integral over r of the partial of f with respect to x plus the partial of g with respect to y dA can be rewritten as a line integral where the integrand is 0 dy minus 2xy squared plus y cubed dx. This means that my line integral reduces to negative the line integral of 2xy squared plus y cubed dx. This matches the partial of f with respect to x plus the partial of g with respect to y, because the partial of f with respect to x when f of x y is 0, And the partial of g with respect to y, when my function is 2xy squared plus y cubed, is the given integrand 4xy plus 3y squared. Now I need to parameterize my path. So my line integral over the path C is negative the line integral over C of the integrand 2xy squared plus y cubed dx. I am going to parameterize each side of the given triangular path. The first thing is to draw a sketch. The sketch has a right triangle with the right angle located at the origin and the horizontal side length of 1 and the vertical side length of 1 aligned with the x and y axes respectively, and then I have a diagonal hypotenuse that goes from the point 10 to the point 01. What I'm going to do is call the horizontal path r sub 1, the diagonal path r sub 2, and the vertical path r sub 3, and you'll notice I've indicated path directions. Remember that my line integrals have an orientation. So my r sub 1 vector is going to be given by the vector t and 0, where t goes from 0 to 1. The r prime gives me dx, which is 1 in this case, because the derivative of r is 1, 0, so that dx, the derivative of the x coordinate, is 1. R sub 2 is the vector given with components 1 minus t and t, with t again ranging from 0 to 1, and my dx in this case is negative 1. And r sub 3 is given by the vector with components 0 and 1 minus t. Again, t goes from 0 to 1, and my dx in this case is 0. So now that I've parameterized each path, I break my line integral up into 3 distinct integrals. The first is negative the integral from 0 to 1 of 2 times t times 0 squared plus 0 cubed times 1 times dt, that's using r sub 1, minus the integral from 0 to 1 of 2 times 1 minus t times t squared plus t cubed times negative 1 dt, that's over r2, minus the integral from 0 to 1 of 2 times 0 times 1 minus t squared plus 1 minus t cubed, all times 0, dt. You'll notice that while there's 3 integrals, the first and the third integral reduce to 0. So that I'm left with one integral, which equals the integral from 0 to 1 of 2t squared minus t cubed dt. That's a straightforward integral, and my integral evaluates as 5/12. Now you get to try it. Pause the video, and given f is equal to the vector with components x squared plus y squared and 0, and r is the set of all points x, y, such that x squared plus y squared is less than or equal to 1, compute the two-dimensional divergence of the vector field, evaluate both integrals in Green's theorem, and check for consistency, then state whether the vector field is source-free. When you're ready, restart the video to check your understanding. The first thing I need to do is compute the divergence of my vector field. The partial of f with respect to x plus the partial of g with respect to y gives me 2x plus 0, or 2x. The closed integral over c of f dotted with n ds is the closed integral over c of f dy minus g dx. The parametric form of x is cosine t. The parametric form of y is sine t. F in parametric form gives me cosine squared t plus sine squared t, which is just going to be 1, and g is equal to 0. dx is negative sine t dt, and dy is cosine t dt, so that my closed integral becomes the ordinary integral from 0 to 2 pi of the quantity cosine squared t plus sine squared t cosine t minus 0 times negative sine t dt. This just reduces to the integral from 0 to 2 pi of cosine t dt, which is equal to 0. This is not a source-free vector field because my divergence is non-zero. This is the flux form of Green's theorem. Green's theorem is extremely powerful in calculus, and it has applications in a huge variety of physical settings. Be sure and let me know if you have any questions about working with the divergence or curl and Green's theorem.